Okay, guys, this is the second half of the review. The first question we're going to do is 10-10. So it says a spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. If the spring is compressed twice as far, what is the ball's launch speed? So the first thing we need to note is that right here, this is the gun and the ball. Right here, this thing only has elastic potential energy, and then right here, it should only have kinetic energy as the ball is leaving, and the spring has been extended as far as it will go. So the important thing here is that the kinetic energy should equal the elastic potential energy. So kinetic energy should equal elastic potential energy, which means that 1/2 mv squared should equal 1/2 kx squared. Alright, so we know that it pushed, the first scenario, it pushed out the ball at a speed of 2 meters per second. The second thing we need to do is, what we're essentially creating here is a ratio, because we say that what happens if we double x? Well, what we're going to do is we're going to use this formula and plug in ones for everything that doesn't change, and we're going to, whatever does change, we'll plug in the appropriate number. We're going to be solving for v. Okay, so the first thing I want you to notice is that the halves cancel, so we're left with mv squared equals kx squared. Alright, so what I'm going to do is I'm going to plug in ones for everything, just to show you what this looks like to begin with. My bad. Got to leave v blank. So we're going to solve for v. So 1 times 1 squared is 1, divided by 1 is 1. So v squared equals 1. V would be 1. This is what we're going to do is we're going to do this again, but we're going to change what it tells us to change. And whatever number we get here is what we're going to have to do to this velocity up here. Okay? So we're going to do this again. This time we're going to do it in blue. We're going to start with the same formula, mv squared equals kx squared. Alright, so we're going to do 1 for the mass, v squared is what we're looking for, k is still 1, x we're going to double, because it was 1 here, now we're going to double it here. So now we get 1 v squared equals 4, or v is equal to 2. Now what this means is we need to double 2. So we need to double whatever we had for our velocity here. So the end result, if we double the distance we push the spring in, the velocity should be 4 meters per second. Okay? So that's the answer. Again, we're trying to do it with ratios. So whenever x was just x, it was 1. Whenever we double x, it was 2. So that means we need to multiply whatever we got by a ratio of 2. Alright, so number 10-11, it's the same basic thing, same basic problem, still got a speed of 2 meters per second, so I'm going to utilize this formula again, or rather this formula again, and what we're going to do this time though is we're changing k. So in this case x stays the same, so kx equals mv squared. We plug in ones originally, 1 times 1 equals 1 v squared. So we get, sorry, that should be x squared. Again, using this formula that we got right here, alright? Because kinetic energy was equal to elastic potential energy. So 1 times 1 squared equals 1 times v squared, and so v would be equal to 1. So this is our starting ratio. So we start off at 1. Now, when we double k, so we change out k, so the new scenario, still kx squared equals mv squared. So we're going to do double k, x stays the same, and that's equal to 1 times v squared. Now, you'll notice that this is 2 equals v squared, or the square root of 2 equals v, which is 1.4 equals v. So this means we need to multiply whatever number we have for our velocity by 1.4. So in this case, it's 2 times 1.4, and that gives us 2.8 meters per second. Alright, there we go. That's number 10.11. Next problem is 10.6. And this says a spring-loaded toy gun launches a 10-gram plastic ball. The spring with a spring constant of 10 Newton meters is compressed. Let's get some data down here first, all right? So let's take some data down as we're reading this. Spring-loaded toy gun launches a 10-gram plastic ball. So mass is equal to 10 grams. We can't leave it at 10 grams. We have to convert it. So we have to divide by 1,000 to get it into kilograms, which is 0.01 kilograms. All right. The spring has a spring constant of 10 Newton meters and is compressed a distance of 10 centimeters. But we can't just leave it like that. We have to change it to meters, so it's 0.1 meters. All right. When the trigger is pulled, the spring is released and shoots the ball back out. What is the ball's speed as it leaves the barrel? So again, we've got this originally, scrunched up spring, ball, and then second scenario, we have an unscrunched up spring and the ball is leaving at some speed v. So what type of energy does it have here? It has elastic potential energy. Here it has kinetic energy. So we set those equal to each other. So we get 1/2 kx squared equals 1/2 mv squared. The halves cancel. So we're left with 10 times 0.1 squared equals 0.01 times v squared. So we solve for this, and we would get 0.1 equals 0.01 v squared, or 10 is equal to v squared. Square root. So the answer ends up being the square root of 10 equals v. All right. Square root of 10, in case you did this, square root of 10 is 3.16. But it'd be 3.16 meters per second as it came out of the gun. All right, next one. 10.12. A particle with the potential energy shown is moving to the right. It has 1 joule of kinetic energy at 1 meter. In the region of 1 to 2 meters, the particle is doing what? So let's look at what's happening to its energy between 1 and 2 meters. Its potential energy between 1 and 2 meters. You should notice that its potential energy between 1 and 2 meters is going down. So this is the way it looks, right? The way the graph looks is something like this. So what we can imagine happening is, in this section, you're pushing the object down into the spring, right? Pushing it down into the string. And then from section 1 to 2, you are showing the object losing potential energy, which means that the spring must be expanding out. That's a terrible spring. Let me try that again. The spring must be expanding out, releasing that object. And then in the end, you show it going back up. So in this section, it's losing potential energy, which means it must be gaining kinetic energy. And if you gain kinetic energy, it means you have to speed up. Okay, so this thing should be speeding up during that section right here. Okay, and again, this is because if you're losing potential energy, you must be gaining kinetic energy. All right, number 11.3. All right, a crane lowers a girder into place. So we've got a crane lowering a girder. For those of you that don't know, it's like a steel beam type thing, into place at a constant speed. So remember, if there's the change in kinetic energy here is 0. All right, and we want to know, consider the work done by gravity and the work done by the tension in the cable. All right, so what's the tension? What's gravity doing? First of all, the force of gravity is going to be pulling this object down, and the force of tension is going to be pulling this object up. So the object is going to be being lowered, right? So the distance, the displacement is going to be going down, which means that, let's just give it a number. Let's say it gets lowered 1 meter, right? So what happens here is that the force of gravity is negative and the 1 meter is negative. So we multiply those together and we get a positive number. So what that means is, since it's going down and gravity is pulling it down, gravity is doing the positive work. Okay, because this object wants to go down because gravity is trying to pull it down. So gravity is doing positive work. The tension, however, is doing, whoops, I can't draw. The tension is doing negative work. And the reason it's doing negative work is because it's resisting the movement of that object. So the tension is resisting the movement. So it's doing negative work. Its work is going to be less than 0 because in this case tension is acting like friction. All right, it's resisting the natural movement of that object. So the answer should be that the work done by gravity is greater than 0 and the work done by friction is less than 0, which would be B. All right, number 11.4. Robert pushes the box to the left at a constant speed. In doing so, Robert does positive, negative, or 0 work on the object. Well, if he's pushing it this way and his force, if he's pushing it this way and he displaces it in the same direction, remember that if the force and the displacement are in the same direction, you are doing work, and he should be doing positive work because he's helping the object move. He's pushing the object in the direction of movement. And so when you're doing that, you're doing positive work. So that's the way you would think about that one. Number 11.6. Which force below does the most work? All 3 displacements are the same. So each displacement there is the same. They give it by a weird symbol R, but don't worry about it. It's the same thing as our displacement. So 10 newtons is going up, and the force, or the displacement rather, is this way. So what that means is that these are at right angles to each other. They're not going in the same direction. So there is 0 work being done here. 0 joules of work being done there. The other one's an 8 joules, or sorry, rather 8 newtons at an angle of 60 degrees. And the displacement is the same. But remember that the displacement and the force have to be in the same direction. So only a component of this force is in the same direction, and that's the x component here. So 8 cosine 60 is the force that you would multiply times this distance. And 8 cosine 60 turns out to be 4 times d. So the work done here would be 4d. And then on this one, see, this one's got 6 newtons, but it's directly aligned to the displacement. And so this work would be equal to 6d, meaning that it should be the 6 Newton force. All right, C should be the answer on that one. Number 8, or rather 11.7, my bad. A light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter. So the important thing here is they're both pushed with the same force for the same distance, which means the work done on the light cart should be equal to the work done on the heavy cart. And so work on the light cart should equal the work on the heavy cart. Remember that work is equal to the change in energy. And the energy in this case that would be changing would be the change in energy, should be the change in kinetic energy. Because notice, this block is neither going up or going down. So if the work done by the light cart is the same as the work done by the heavy cart, their change in energies should also be equal. I can't spell heavy, light. Alright? Should equal the change in kinetic energy of the light. So the heavy cart's change in kinetic energy should equal the change in kinetic energy of the light cart, again because both of their works are the same. And so they should be equal to each other. Alright? Number 11.13. What power motor is needed to lift a 2,000 kilogram elevator at a steady 3 meters per second? Well, remember that power is equal to work divided by time, but also remember that force times distance divided by time is equal to power, because work is force times distance. Then remember that distance divided by time is equal to velocity. So what we need to do is to find the force that's having to be lifted times that velocity. So force that's being lifted is the force of gravity, which you should remember is mass times 10. So the force of gravity times V, which should be, in this case, 20,000 newtons, because you're multiplying 2,000 by 10, times 3, which would be 60,000 watts. Okay, so that should be his power rating. Alright, and on the answer there, it gives it as 58,800. That's because they used 9.8 as their, they multiplied it by 9.8 rather than 10. So it made that big of a difference on this particular problem. Alright, but this is how you work that one out. Alright, so this is all the problems. Hopefully, if you've gotten this far, you will do well on the test tomorrow. I wish you the best of luck. Remember to please send me an email or a tweet if you have any further questions.